In this video, I want to talk about one more consequence of the basis for the column space that we found. This consequence is expressed as what's called a matrix factorization. So say we have some matrix A. It can be an arbitrary rectangular matrix. Say it has m rows and n columns. And say that it has rank r. So the dimension of the column space is equal to r. This theorem says that if A has rank r, then we can write A as a product of two matrices, x and y. Now x is going to be a matrix with r many columns, and y is going to be a matrix with r many rows. So if we look at the dimensions of things, this check out, right? Because if we multiply x as m by r, by y as r by n, we obtain an m by n matrix, the same dimensions as A. So this theorem says that if A has rank r, then we can write it as a product of two matrices, x and y, where x has r many columns and y has r many rows. Now what's so great about this theorem? Well, this is actually how we can compress matrices with low rank. So normally, if we're going to store the matrix A, well, since it has m times n many entries, we would have to store m times n many numbers. Now instead, we could just store the matrices x and y, and then when we want A, we can just multiply these matrices together. Now to store x, since it's an m by r matrix, we have to remember m times r many numbers, and to store y, it's an r by n matrix, so we have to remember n times r many numbers. So in total, we have to remember this many numbers. In other words, r times m plus n. Now if r is small, then r times n plus n can be much, much less than m times n. So that means that we have a lot of savings in just remembering x and y rather than A itself. Okay, so let's go ahead and see how this theorem works. I'm just going to illustrate this theorem with an example. So A is the matrix whose first row is 1, 2, 3, 5. Second row is 2, 4, 8, 12. And the third row is 3, 6, 7, 13. Okay, so this is our matrix A. And now we saw that the first column, A1, and the third column, A3, were a basis for the column space of A. So that means that we can write all of the columns of A as linear combinations of A1 and A3. Well, let's go ahead and do that. So A1 is, of course, just 1 times A1 plus 0 times A2. A2 we saw was equal to 2 times A1 plus 0 times, I'm sorry, this should be A3. Let me go ahead and erase that. This should be A3, 0 times A3 here as well. A3 is of course equal to 0 times A1 plus 1 times A3. And A4 is equal to 2 times A1 plus 1 times A3. Let's see if that checks out. 2 times A1. Yes, that looks good. Okay, so now let's let X be the matrix consisting of the first and third column of A. So this is going to be the matrix whose first column is 1, 2, 3. And second column is 3, 8, 7. And now we're going to let Y be the matrix whose columns are these linear combinations. So the first column of y is going to be 1, 0. The second column of y is going to be 2, 0. The third column is going to be 0, 1. And the fourth column is going to be 2, 1. Okay, so now if we look at the product of x and y, well, the first column of this product is just going to be x times the first column of y. And when we take the product of a matrix and a vector, we just use the vector to give us a linear combination of these columns, right? So the first column of x times y is going to be just the first column of x. So that's 1, 2, 3. The second column of x times y, well, this is going to be 2 times the first column of x. So that's 2, 4, 6. The third column of x times y, that is just going to be the second column of x, 3, 8, 7. And now the fourth column of x times y, that's going to be 2 times the first column of x plus the second column of x. So that's going to be 5, 12, 13. So you see that x times y is exactly our original matrix A. So in general, how this theorem works is we can just let x be the columns of A that span the column space of A, and let y be the coefficients in the linear combinations that give us each of the columns of A. And then when we have x times y, we're going to get back the matrix A.